As we get into larger systems of equations, we can still use a method of elimination to solve them, but it gets more complicated with the larger number of variables. And so because of this, we turn to using something called matrices with row operations to solve a system. It helps to keep things a little bit more organized, and the more variables you have, the more efficient that the matrices are going to be. So we're going to look at several steps for setting up the matrix, and then I'll show you how to use the row operations to solve them. So to begin with, when you set up what's called an augmented matrix, you are only going to put your coefficients and your constant into that matrix. And you're going to separate your constant from your coefficients with a line, and so you can think of that line representing the equal sign. So as I look in this particular system of equations, my coefficient of x right here is understood to be a 1. So in my matrix, I'll start with a 1. And then if I look at my coefficient of my y, it is also, when there's nothing there, understood to be a 1. So I'll put another 1. And then finally, when I look at my coefficient for the z, don't forget the little negative there, that is understood to be a coefficient of -1. So notice I'm not putting the variables, I'm simply putting the coefficients. Now, the line in the matrix represents the equal sign, and then your constant will go on the right-hand side of your equal sign. So if I now look at my second equation in this particular system, the coefficient of x in this case is a 3. The coefficient of the y in this case, don't forget the negative that's there. Oops, I kind of covered up the negative, so give me just a second. If I look at the coefficient of the y, we'll take the negative with it. So the coefficient would be understood to be -1. And then finally, if I look at the coefficient of z, that is understood to be a +1. And then the constant for that particular equation is -6. So then I go to my third equation, and in front of the x, it is understood to be a 1. In front of my y, we have a negative and a 4. And then finally, in front of my z, we have a +2. And then the constant for that particular row is -43. So that is how you set up the system into what is called an augmented matrix. Now, let's talk about our goal. The whole goal of this particular using matrices to solve a system is you want to end up with a 1 in the top left-hand corner, and then followed by 2 zeros below it. And then in the second column, you want a 1 in the second row, second column, with a 0 above and below it. And then in the third column, you want to get a 1 down at the bottom with zeros above it. And then, of course, to the right, there will be other numbers sitting there. Now, let's talk about why that is our goal. If we translate this back into equations, on this first row, remember the first number represents the coefficient of x, the second number is the coefficient of y, the third number is the coefficient of z, your line is your equal sign, and then of course you have some constant over here. So 1 times x would be x, plus 0y, plus 0z. So basically, we will, on that first row, we will know the solution for x if we are able to reach our goal matrix. When you look at this second row, you would have a 0x plus a 1y plus a 0z, and again, that's going to equal to some constant over here. So basically, the second row of that particular matrix will tell us the value of y as part of the solution to that system. And then when we get to the bottom row, you would have a 0x plus a 0y plus a 1z, and that would be equal to some constant. So in a sense, the bottom row tells us the value of z. Assuming that you can reach that goal, this particular system would have one solution, and these values would be determined by your ending result matrix. Now, if for some reason you're trying to reach the goal and you can't reach it, let's say that you're doing something and all of a sudden you get a row of complete zeros like that, remember that if you have a true statement such as 0 equals 0, that's an indication that you've got some infinite solutions. You've got lines overlapping. Whereas, let's say you're moving along and instead of a true statement, you get something such as, say, a row of zeros and a 6. Well, that would be a false statement, and a false statement is an indication of no solution because you have lines that are parallel.